Okay, so welcome to this lecture. We started on boiling in the last lecture, if you recall, that boiling and what is evaporation. So, we said boiling always involves the formation of bubbles. Now, there are two classes of boiling basically. One is basically called subcooled boiling. If you look at the text over here, one is called saturated boiling. Now, what is subcooled boiling? Subcooled boiling is that when the liquid temperature starts below the saturation temperature. So, the bubbles actually grows on the surface, it detaches, but it then kind of becomes smaller and condenses as they traverse. So, the liquid temperature is below the saturation temperature. So, essentially the bubble grows, detaches, becomes smaller due to condensation and then just goes off, right. When the liquid temperature is equal to the saturation temperature, right, we get what we call saturated boiling. In the saturated boiling, what happens is that the liquid temperature equals the saturation temperature. So, the bubbles, they grow, they detach and they traverse unharmed, basically unaltered in size. So, the bubbles travel in an intact fashion, right. So, these are the basic two differences between subcooled boiling and saturated boiling. So, these are the two major classes. This is the most important curve that you will encounter in boiling. Okay, so, boiling, this is basically the degree of superheat. Degree of superheat is nothing but the wall temperature away from the saturation temperature, right. Okay. And this is the heat flux. So, what happens is that when the excess temperature, that is a wall temperature minus the T superheat, T saturation is less than 5 degrees Celsius, that means less than this mark, what you have is that there is no boiling at all. The heat transfer is by natural circulation, right. So, it is like basically a problem in which you have a heated surface underneath. So, there is a circulation current that is created, right, because the layer of liquid near the surface gets heated, it loses its density, it climbs up, okay, and then it comes down once again, gets cooler, comes down. So, you get set forward basically a recirculating stream, right. So, there is no boiling, but the heat is transferred solely by natural circulation, right. If on the other hand the excess temperature is greater than 5 degrees Celsius, if you look at this point A now, what do you see? You see the first instance of bubble formation, and this is called nucleate boiling. Nucleate means the bubbles actually nucleate from the surface. So, if you have a surface like this, you will see that there are bubbles that will form on the surface like this, right. So, these bubbles form at the heater surface. So, this is basically your heater or the wall, because you are heating the wall, right. And the heater surface, these bubbles usually form from the micro cracks on the heater surface. So, if you look at this heater surface in a macroscopic view, it might look very smooth, right. If you take basically a microscope and start to look inside, you will find that there will be these cracks of different kinds, and these cracks will have dimensions which will be like D will be of the order of say 10 micron, 100 micron, etc., right. So, these cracks basically serve as nucleation points. So, the bubble starts to grow from these cracks. This is because when you actually put a liquid over this heater surface, the liquid cannot always penetrate through these cracks, right. So, there is some entrapped vapor in this crack, right. So, that actually leads to this nucleation of bubbles. These bubbles grow, detach and migrate towards the free surface, okay. So, till this point B on this curve, okay, and you can see there is a steady increase in the heat flux because more and more number of bubbles are forming, right. So, around B, when the degree of superheat is about 11-12 degrees, okay, you will find that till this point the bubbles were mostly isolated. So, these bubbles were very separate from each other, right. As they were moving up, they were very separate from each other, right. So, they were not cross talking, like we saw in the case of droplets that they were not cross talking. Here also the bubbles actually do not cross talk with each other, okay. So, the bubbles till the point B are basically isolated, they do not interact with each other, but beyond point B, okay, you get more and more nucleations of bubbles that starts to happen. So, these spaces starts to become full of bubbles, okay. These bubbles merge with each other and form columns of vapor, Okay. So, you will not be able to see these single bubbles anymore, you will be able to see these slugs of vapors that are going up. Okay. So, this decreases the heat flux from this point decreases the surface area. So, the slope of the curve starts to decrease, you reach a critical point C, okay, where the slope reaches some kind of a maximum. Okay. So, C is called basically the critical heat flux. Okay. So, you start to form these slugs and columns, you get to the point C where the heat flux is kind of maximum, okay, but the slope of the curve starts to decrease at that particular point. Okay. So, as the temperature increases beyond the critical flux, okay, the rate of bubble generation exceeds the rate of bubble detachment from the surface, right. So, that means if this is a surface, okay, before these bubbles actually detach from the surface, more and more bubbles starts to form, okay, from the same place. So, the generation rate exceeds the detachment rate. Okay. So, the bubbles, what it happens is that from multiple sites, even before they detach, they start to form, they start to coalesce with each other, right. So, these bubbles starts to cross talk with each other even before they are detaching, okay, from the surface. And what they do is that they form a film, this is like a vapor film, okay, over portions of the surface, right. So, this decreases, what this does is that it is like a vapor cushion that you have formed, right. So, there is no direct contact now between the liquid and the heated surface, right. So, there is no direct contact, as a result of that the contact area basically reduces, okay. And so, naturally what tends to happen is that now the heat has to be transferred through this vapor layer. So, the heat from the surface goes to this vapor, from the vapor it goes to the liquid, okay. And these vapor films, however, are not stable, they can detach from the surface and lead to restoration of the liquid and the resumption of nucleate boiling. So, what happens is that these vapor films can actually get detached from the surface also, okay, and fresh liquid can come and wet the surface, okay. So, you get a reinitiation of this nucleate boiling, okay. So, because it involves this kind of an unstable film and a partial nucleate boiling type, this is basically called the transition boiling in this particular case, right. So, this is called beyond the critical heat flux from C to D, if you look at it, this is basically called the transition boiling. Transition boiling involves what? The bubbles from the nucleation sites basically cross talk with each other, because there is a lot of bubble generation that happens, because the degree of superheat is really high, it is of the order of 30 to 320, you can see from that graph, right, it is from 30 to 320. So, it is really what happens is that this bubble starts to cross talk with each other, they merge, they form a vapor film. Now, this film may not be stable all the time, right. So, sometimes this film gets detached, fresh liquid comes and wets the surface and you get nucleate boiling. Sometimes this film actually acts as a cushion, okay, preventing the liquid from coming in contact with the surface, okay. So, that actually leads to what we call a decrease in the corresponding heat flux values because of the formation of this vapor film, right. Okay. Now, when the excess temperature becomes high enough to sustain a stable vapor film, this was unstable, right, the heat flux reaches its minimum. This point is called the Leidenfrost temperature. This point is basically called the Leidenfrost temperature, okay. So, the vapor film, what happens is that it was unstable, at one point of time it becomes really stable, that means the vapor film is stable, it does not get detached from the surface. So, that corresponds to the minimum heat flux limit, and the temperature and that particular point is basically called the Leidenfrost temperature. At temperatures above the Leidenfrost temperature, if you go above the Leidenfrost temperature, the bulk liquid and heating surface becomes completely separated by a vapor film. So, this is called basically film boiling. The phase change in film boiling occurs across the liquid vapor interface instead of directly on the surface. So, there is a liquid and a vapor, that is how the heat is transferred. So, if this is the surface, there is a vapor film of delta that is sits over it, and then you have the liquid. So, it is not heat directly transferred from there to there, it passes through this vapor layer, Okay. So, it is basically a liquid vapor interface across which the heat is transferred. Okay. So, the thermal energy from the heating surface reaches the liquid vapor interface by convection in the vapor film. So, within the vapor film there is convection, and that is how you actually get to the interface. It can also happen by direct radiation. Now, in the film boiling regime, the heat flux becomes a monotonically increasing function of the excess temperature. So, in this regime the heat flux goes up like that. Okay. So, the heat first goes to the vapor film, the vapor film actually gets heated, it transfers the heat to the liquid either through interfacial processes or through radiation, right. So, that is how the film is actually done, and this is called regime 4, which is called the film boiling. At the end of this regime 4, you can have the catastrophic limit also, right, because you can see the degree of superheat is very, very high, right. Because the degree of superheat is very high, the material of the heating surface may actually melt. Okay. So, you have a catastrophic situation. In many of the cases, this boiling is done by putting in a wire, a heated wire within the liquid. Okay. So, this wire actually acts as the heated surface, and you get all the events like nucleation. So, what happens is that this wire actually melts. So, it just detaches. Okay. So, you just have the end of the whole process. So, material integrity is one of the key factors, okay, when you look at that kind of a regime. Okay. So, here of course, we assume that the surface temperature is the independent variable and heat flux is the dependent variable. In most of the cases it is the other way around, right. You control the heat flux and the surface temperature adjusts accordingly. Okay. So, these are the 4 regimes. Let us just revisit once. Initially you have no boiling, then you start having isolated bubbles, then you actually start to having slugs and columns that goes up. Here the heat flux becomes maximum. Then you have something called a transition case, in which there is a vapor film that actually forms over the surface, but that vapor film is unstable. So, it is on and off kind of a vapor film. You get to a situation when you actually have a stable vapor film, that is called the Leidenfrost limit, and then you slowly have this increase in the heat flux, because you go to the film boiling regime, where there is a vapor basically that guards the fluid, the liquid, from the heated surface. So, the heat is transferred not from the surface directly to the liquid, it is actually transferred to the vapor film, and the vapor film through convection and radiation basically transfers the heat across the liquid vapor interface to the liquid. So, that is what happens in this particular case. Okay. So, these points should be, this is the critical heat flux, this is the Leidenfrost point, and there can be the catastrophic limit at the end of the journey. Okay. So, so now there are different other cases of boiling also, okay, that we will see over here, that there are 2 different classes of boiling apart from the point that we mentioned already. Like there can be boiling due to surface imperfections, which we already said, okay, that is the surface has got this micro cavities like this. This is a zoomed in view of a cavity, and this length scale can be of the order of microns, hundreds of microns. It can be of the order of 1 millimeter also, depends on what surface you are dealing with. This leads to what we call bubble embryos that grows through evaporation. Okay. So, it leads to an inception of a bubble, that is like an embryo, right, and this bubble slowly grows, like the entire growth process has been shown in this particular diagram. Such boiling is called what we call heterogeneous nucleation. So, it requires a surface. Now, the last lecture, if you recall, that we saw that the droplets actually undergo this kind of diffusional entrapment induced boiling, that is called homogeneous nucleation. In homogeneous nucleation, what happens is that, say you are dealing with a pure degassed liquid. Okay. Now, bubble formation in those cases happens at the molecular vapor clusters, okay, within the bulk liquid. This is called homogeneous nucleation. That means there is no surface involved, but this requires a substantially higher level of superheat, which we already said over here, that the degree of superheat can be almost as high as the critical temperature, right. So, the degree of superheat is very important in those cases. In the case of heterogeneous nucleation, however, when you have particles where you have some media on which these bubbles can actually grow, right, So, that is called heterogeneous nucleation, and the degree of superheat requirement is very low, as you saw in the boiling curve, right. Beyond 5 degrees Celsius you start to have bubbles, right, but you cannot have the same thing when you actually have pure degassed liquid, because in those cases you can only have homogeneous nucleation, right, that is happens at the molecular vapor clusters, and that requires a substantially higher level of superheat. Okay. So, what we learnt is that these are there is subcooled boiling, there is a difference between boiling and evaporation, subcooled boiling, saturated boiling, then the boiling curve, which is the most important thing that you would get, and this is a very typical boiling curve. This is done for water, saturated water. It can be done for other types of things also, and we learned the different stages of that boiling, and now we know that there is something called heterogeneous nucleation and there is something called homogeneous nucleation of the boiling, right. Okay. And so, what we are going to do right now is that we are going to study that what will be how we can analyze these kind of problems, okay, in a little bit more details, right. Okay. So, let us go and do that. We start with a problem in which a vapor bubble, and this would be not very difficult, a vapor bubble, okay, is immersed, okay, in its own liquid, okay, in its own liquid, okay, and can contain non-condensable gases. So, if you look at, for example, this, the problem is somewhat like that, this particular figure. Okay. Let me just pull it up. So, this is basically a vapor bubble. This is immersed in its own liquid. Okay. The pressure and temperature inside the bubble, this is R, the radius of the bubble, this is R at any other location outside the bubble in the liquid. So, this vapor bubble is growing, this is a homogeneous nucleation of the vapor bubble in a superheated liquid. So, that is the problem statement, right. Okay. So, that is the problem statement that we are dealing with, is a homogeneous nucleation of a vapor bubble in a superheated liquid. That is what we are going to study in this particular problem. Okay. And then we are going to see that how other types of bubbles actually grow. Okay. So, now you understand. So, we are going to study this. So, we write the Laplace-Young equation, and this can contain condensable gases. So, that is why you have retained this term Pg over there, right. So, it can have non-condensable gases, as we can easily see that Pg plus Pv is greater than Pl, right. So, this essentially implies one and only one thing, that the higher vapor pressure inside the bubble causes more number of molecules strike the interface from vapor side. Okay, from vapor side, where they are absorbed by the liquid. Okay. So, now to maintain a mass balance, right, because mass has to be maintained in equilibrium, maintain mass balance. Okay. There must be a corresponding increase in the number of molecules emitted through the interface from the liquid side. Okay. From liquid side, there has to be has to be an increase in number of molecules, right. Okay. So, this leads to one thing, this leads that the liquid near the interface needs to be superheated above the saturation temperature. Okay. So, the liquid near the interface, remember near the interface, mark the words, near the interface needs to be heated, okay, above the saturation temperature. Got it? It needs to be heated above the saturation temperature. Okay. Now, if you recall, for a bubble, for a curved bubble basically, for a curved bubble, this, if you recall your old notes, you will see that the vapor pressure within a curved bubble is given by, do you recall this particular thing, this we covered. So, all these things you can see how it comes in handy as we go on in the course. This is rho v, PV sat different temperatures, RB into rho L. Usually this particular term is much less than 1. Okay. Because it is less than 1, then this exponential now can be expanded in a series function. So, PV is equal to PV sat at temperature to 1 minus 2 sigma into rho v divided by PV sat RB into rho L. Okay. Got it? Okay. Now, if you combine you can write Pg plus PV sat minus PL equal to 2 sigma by RB to 1 plus rho V by rho L. Okay. Now, we already can make use of the Clapeyron equation, which gives you basically dP by dt, if you recall, HLV T into 1 by rho V minus 1 by rho L. Now, you know that rho L is much greater than rho V, and you can also invoke the ideal gas assumption rho RT. So, this will give you, combining all this will give you dP by P is equal to HLV divided by RG T square dt. Let us call this equation 1. It will come in handy later. Okay. Now, for pressure change from PL to PV sat T and temperature change from T sat to T, we integrate equation 1 and we have this ln PV sat T divided by PL equal to HLV by RG T sat T minus T sat divided by T. Okay. Now, you already know Pg plus Pv sat T minus PL is equal to 2 sigma by Rb into 1 plus rho v by rho L. You substitute that over here now. Now is the correct time to substitute this. What you get is that T minus T sat, which we can mark as delta T, is Rg by HLV T sat into T ln 1 plus 2 sigma by PL into Rb into 1 plus rho v by rho L minus Pg by PL. I am sorry, this Pg by PL. Okay. So, this is the complete thing that you get. This particular term is much less than 1. This is of the order of sorry, not this particular term, once again, not just this term. Okay. This particular term, only this one, is much less than 1. This particular term over here is almost equal to 1, because rho v by rho L is a very small number. Okay. So, what you get is that delta T is equal to Rg T sat into T divided by PL into HLV 2 sigma by Rb minus Pg. Okay. Okay. Now, this is the important expression, that is the degree of superheat that is required. Okay. Then we will find out a few more things about it, like for example, what will be the critical droplet diameter, critical bubble diameter. So, if there are no condensable, if there are no non-condensable phases, condensable gas, that means your Pg is equal to 0, okay, you can cast Rb, okay, which is the critical, we will define it just shortly, 2 sigma into T sat divided by HLV into rho v into delta T. So, this is the expression that you get. This is the critical radius required for a bubble to exist at delta T above the saturation. Okay. If R bubble is less than Rb, it collapses. If R bubble is greater than Rb, it grows. One other thing to mention is that Rb becomes actually smaller as delta T goes up, that you can see from the inverse relationship that you have, that with increase of degree of superheat, the critical droplet sizes also, critical bubble sizes also grows up. Okay. Now, Griffith and Wallace, what they suggested was that, so this is for homogeneous, right? Griffith and Wallace actually suggested that this is also applicable, for nucleate boiling. Nucleate boiling from a surface, from a microcavity. Okay. In that particular case, this Rb is given by the cavity opening, this mouth of the cavity. So, it is basically the mouth radius or diameter, whatever you call it. got it. Okay. So, that is an interesting argument that was provided, okay, that why does how does a bubble actually grow, how does a bubble immersed in a liquid of its own kind, essentially how does it actually grow, and this also gives you a significant analysis that what it can actually show. Okay. So, let us see. So, we have done this particular portion on this bubble. Here there is one interesting thing that we would like to point out. So, this is for example from a crack tip, how does a bubble grow, that we have already specified over here. Now, if the interface if we consider K as the curvature of a liquid vapor interface, the curvature of liquid vapor interface. Okay. Now, if K increases with increase in vapor volume, so it is a curvature of the liquid vapor interface. Okay. So, just take a look at this particular curve, right. So, if K increases, okay, with increase vapor volume, say if the vapor volume is V, if that increases and K increases, then we call that this is a stable. Okay. But so it is, for example, between A to D, you can see this particular curve, which is basically the curvature versus the volume. This is an increasing function, so it is stable, right. Okay. Nucleation happens when K actually goes down as V goes up. So, in this particular regime or this particular regime or this particular regime, when K actually goes down, that is the curvature of the liquid vapor interface actually goes down with increase in volume, that is the time when you start to have nucleation, okay, beyond the point D, where the curve after the curvature reaches its max, right. So, in these cases, if that is the case, again moving on to this, if that is the case, then this delta T is written as T by T minus T sat is equal to 4 sigma T sat divided by PV HLV into DC into K max. This is the diameter of the cavity mouth. Okay. So, that is what the key significance that we have. Okay. So, now in the next thing is that now that we know that what the bubble does, let us look at the bubble dynamics now. Now, we know how a bubble can actually form. So, we can look at the bubble dynamics in two ways. In one case, the bubble grows in quiescent superheated liquid. That is what we did just a moment ago, right. I mean we established what is the critical diameter, and the bubble grows on a heated wall, So, this is homogeneous nucleation, this is hetero. Okay. So, we are going to study this particular thing in details now, okay, so that we can see that what is actually going on. Okay. So, in the next lecture what we are going to do is that we are going to look at this particular phenomena in more details, okay, and we are going to see that there will be first we will take the homogeneous nucleation situation, and we are going to see that there are two basically growth phase, one is inertial, okay, and the other one is heat transfer controlled. So, you will see what each of those phases actually look like. Okay. So, we will see in the next class and see that how we proceed from there. Okay. Thank you.